Welcome back. In this lesson, we're going to look at two different things. We're going to look at the difference between density and specific gravity, which is one way to measure the density of a rock. And then we're also going to look at a few more of the properties of rocks that we haven't covered in the past. Okay, so the first thing I'd like to talk about is density. If something is dense, you've got more stuff in a space than something that's not dense. So let's say I have a box of any size, and I put some feathers in that box or some cotton in that box, and the density of that box would be very low. If I would fill it full of bricks or fill it full of rocks, you would have the density of that box being very high. So you're doing a math problem, simple one, the mass of that material, so let's say the mass of a rock in grams, divided by the volume of that box. So you would take its dimensions and find its cubic dimensions, so cubic centimeters, cubic meters, whatever that dimension would be, and then you could have, for instance, the density of something being grams per milliliter or grams per cubic centimeter, something like that. That's the density. And so every object has a density. You have a density. Okay, your mass divided by the amount of space your body takes up is the density of your body. Specific gravity is a little bit different. Specific gravity is a ratio between the density of an object. So let's say I have a rock and I find out its volume. Okay, I find out its volume usually by putting it in some water and then letting the water go up in a graduated cylinder that has markings on the side. As I put the rock in, the water goes up by the same amount as the rock's volume is. So you can simply subtract and then find out what the original volume of the rock was. Then weigh the rock, usually before it's wet, and then divide it out and you can find the density of the rock. Specific gravity is a ratio. So you find the density of the rock, density of the mineral, whatever you're looking at, and then you divide it by the density of water. So it's really a comparison. Not a comparison of densities to each other, but all to the same thing. So it's essentially apples to apples. You're comparing the densities of different rocks by comparing them each to the density of water, which never changes. And then as a result, you can compare those specific gravities. So when I think of specific gravity, I'm thinking of density, but it's a little bit of a difference between the idea of density and the specific gravity of a rock. So you're using specific gravity in many ways to find out what rock it is. So you're diagnosing or making a prediction of, I think I've got this rock or I think I have this rock. Many ways, if you're experienced with working with a rock a long time, you'll say, oh, it has this weight. So you would know the difference between, say, aluminum, which makes pop cans, and iron. So if you had a piece of aluminum the same size or the same dimension as your iron, you know just instinctively that iron is going to weigh more in your hand than the aluminum does. Well, it's essentially the same. Your specific gravity, your knowledge of how hefty or how weighty it is per size, for its size, is what you're using to figure out what rock you've got. Most minerals have a specific gravity between 2 and 3, right? So if you were to have a glass of water and a rock of the same size, which weighs more, okay? Well, your rock normally is 2 or 3 times what that same amount of water would be. And some are even very dense. So for instance, gold is extremely dense, 20 times that of water. So for the same amount of water, like if you were to have a gallon of water, a gallon of drinking water, and you had a gallon jug full of gold, that you know what a gallon of water weighs. You've held it, so you know what it weighs. Gold would be 20 times that weight. Now we've looked at several properties before in previous lessons. We've looked at luster, if you remember. That's how light reflects off of it, whether it's shiny or dull, etc. We also looked at whether light would go through a mineral. It could be clear, it could be translucent or transparent, something like that. It can transmit light. Minerals have colors, so that's one. Sometimes it's a way that you can diagnose a rock. Streak, if you remember, if you make a streak mark on a piece of clay tile, what you're doing is grinding that rock and making a powder and then kind of marking it using it like a crayon. That's a way that you can find out what material you have. We also looked at the shape of the crystal, or it's also called its habit. So today we're going to look at a few, I don't know, simpler ways or other possible ways that you could diagnose a rock, figure out what rock that you have. One is by taste, and I wouldn't suggest you put every rock in your mouth, but certain chemicals will have certain tastes. For instance, a mineral that is alkali or basic as opposed to acidic usually has a sourish kind of bitterish kind of taste. So in some ways you can figure out what you have by tasting. Smell works the same way. Not that you should directly whiff into every rock, because sometimes the materials could actually hurt you that way, but you can generally in the direction kind of smell that rock, and one rock does have different smells in some ways depending on what minerals you've got. Another possibility is if you have something that you could use like a magnet. Let's say you have lots of iron in a rock. Well, that magnet will be attracted to that iron, and actually there are some rocks that would stick to the refrigerator. They're just natural magnets. So you can use a magnet to find out if there's high iron content. The other one is it can bubble. For instance, if you put acid on it and you have some kind of a carbonate, some kind of a limestone, it will bubble or fizz when you put a dilute acid or a weak acid dropped onto it. It would bubble and fizz and create some carbon dioxide gas. So that's one way if you do an acid test on it, and these would be called tests. You do this test on it, you get these results, that leads you to believe, hey, it's probably this or that, and you can change out. The last one is called double refraction, and I'm going to show you a little film clip. It's also called biofringence. So let's look at that.
Here is a single red dot on a white piece of paper, and here is a piece of calcite crystal placed on top. Notice that the single red dot appears as two separate dots. This is because the two separate polarization components perpendicular to each other are refracted in two different directions by the calcite crystal. And this can be shown with this piece of Polaroid. There is one of the rays, one of the images of the red dot. Here's the other. This is called birefringence or double refraction.